Okay, good morning. Good morning. Can you hear better now? I spoke so loud that it doesn't make any difference. Ron? It's no? Okay, because it's Is it fine? Okay, good. Yeah, so I thought it would be really easy because I'm actually giving a course where I teach some type theory and some Agda. I didn't realize, that I was not the only one who was going to speak about type theory. I realized Bob was going to give an introductory course in type theory. There would be supporting lectures in category theory and proof theory. So I thought, this is not a course on programming languages with one course independent type theory. This is a school independent type theory. Well, how wonderful, how far the world has progressed. Especially for me, who has been around for a long time, I've seen, the development from the early 1980s when there were really only two groups in the world who did this kind of thing, and they had just started. It was the group in Gothenburg, Chalmers University of Technology and the University of Gothenburg, and the group at Cornell University led by Bob Constable, who you will have the pleasure to hear later this week, and where Bob was a PhD student. These were the only places who did dependent type theory at the time, and since then we have had a real explosion, or maybe we shouldn't say explosion, maybe we should a gradual growth, We have taken one place after another, In the early 90s, we started something called the TYPE project, supported by the European Union. And in the beginning, we were maybe 8 sites or something. By the end of the funding of that project, we were maybe 30 different universities in Europe who were doing this thing. We see a lot of evidence of the success, like that the Coq system received the ACM Software System Award, which is, of course, a recognition by the general community, not only by ourselves. So it's really very, very, very gratifying. But of course, I had the problem a little bit. Okay, so I have to prepare some new material. But it's a nice question to ask yourself. Now you actually have to give a course which is a little bit more of an advanced course in type theory. What would I teach? So I started thinking, well, what would I have liked to learn about this? I have somehow gradually over the years learned bits and pieces of it. What do I consider most important? So I've been trying to think about that, and well, you will see what the result is. But I should also point you to my home page. I've started putting up some material on my home page, so you can just Google my name, and there will be various links. I haven't got onto internet myself yet, so I can't show you, but you will easily find quite high up on the home page a link with material for the OPLSS 2015 summer school, and there will be, among other things, a draft version of an article for the Stanford Encyclopedia of Philosophy. It's not yet published, but it's going to appear soon, which is, an entry for that encyclopedia about intuitionistic type theory, written by myself and Erik Palmgren, who is a logician from Stockholm. So in writing this article, I also had to think about, what should be in such an article. What are the most important things to tell people who are curious about intuitionistic type theory? What should they learn? So it's of course a related question to to ask myself, what should I try to teach you? It's of course a different thing in the sense that that's a little bit, it's not sort of a lot of technical detail, but a lot of overview of important things. But I think still it's appropriate background material for you to read. Some of it is very elementary, some of it is very advanced in the sense that you already need to know, for example, quite a bit of category theory in order to know about categorical models for type theory and so on. So on this website, I also have some articles by Per Martin-Löf. Which are well worth reading, because Per Martin-Löf is in a sense the founder of the field. He wrote type theory. Yeah, he has, I haven't put up them all, but the years you should know, is 1971, 1972, 1973, 1979, and 1986. So these are the main versions of type theory that he presented. They are all different, and they represent his search for the formulation of something really important. His first attempt was inconsistent. He tried to have a theory with a type of all types. And then maybe Bob has or someone has already told you that this was inconsistent, was discovered by French logician Jean-Yves Girard, who found that you could encode the so-called Burali-Forti paradox in this theory and show inconsistency. In 1972, the first was inconsistent. In 1972, he introduced a so-called universe, a type of small type, and made the theory predicative. I don't know, has anyone talked about the issue of predicativity, impredicative? So I will talk more about that in a little bit. But what I can say at this stage is that impredicative definitions, when you somehow define something by quantification over a collection containing the notion that you are actually defining, you may be in trouble. This is the sort of thing that led to the Russell paradox, and it's also the thing which led to this paradox. So predicative is to try to avoid such definitions, and the way this is done by introducing a universe is by distinguishing between small types and large types. I can see from the that you have had some discussion of that in category theory, because that's where this distinction comes from in the first place. This is a very good version of type theory, a very basic one, and this is actually what we decided to present as the first main version in the Stanford Encyclopedia article. It's a somewhat small version, but it's still very, very basic. It has no identity type. You have to define identity yourself everywhere. So no identity type. In 1973, he tried a new version. He wasn't satisfied with this. Here he introduced an identity type. And he introduced also a whole hierarchy, an infinite hierarchy of universes. In 1979, he wrote the famous paper, which is on this web page, called Constructive Mathematics and Computer Programming. I think this is really the milestone, because it contains three important things. The first important thing is that it discusses the relation between constructive mathematics and computer programming, and it comes out with a slogan, which I will write here, that they are the same. It's the same to write programs, if you by programming mean program something with a given specification, and constructive mathematics, where the functions you actually define are programs. And this is somehow the guideline for this whole field that we are in. We are somehow in the process of unifying mathematics and programming. Maybe this is the future. Since so many of you are here, I think you think so too. We will see, we will see. But it's a very exciting prospect that somehow the borderline between these two kind of activities are kind of get blurred. And this is discussed in a very nice way in this paper, so you should really read that paper. There is also the definition of what's called extensional type theory. So I haven't checked enough of the details of Bob's lectures in order to know whether he discussed this distinction. So I will, and Bob Constable will, because the new Perl system works in this tradition. And then it contains something which is very, very important, but which it is very, very difficult to make people appreciate. It's something called meaning explanations. It's somehow Per Martin-Löf turning philosopher, if he was not that from the very beginning, because his whole way of writing is very much like that of a philosopher. But it is the explanation, somehow the basic reasons why type theory is meaningful. Meaningful in a sense which was somehow started to be explained by, the founder of constructivism, Brouwer. This is like early 20th century. So it's continuing this tradition and making this more precise. Why is it that the things we say in type theory have a clear meaning? Why is this somehow a much more sophisticated and detailed approach to the foundations of mathematics than the generally held views? Usually one talks about formalism and Platonism as views of the foundations of mathematics. Constructivism or intuitionism is yet another way. And the way in which this kind of gives a clearer meaning has very much to do with the fact that you can understand it in terms of programs computing certain things, you being able to observe certain things. So I will come back to that later in my lectures. So this is something very important which was much clarified in this 1979 paper. So I would say that this is a milestone. Those are all preliminary attempts. Except that a few years later, in 1986, he changed his mind. He said, I was all wrong. Equality should not be extensional, because if equality is extensional, then the system becomes undecidable. It's not decidable whether, if you have a judgment, I think Bob has used this term, right? Yeah. we have a judgment that a certain program or element has a certain type. Then in extensional type theory, this is undecidable. You can't sort of give an arbitrary term, little a, and type big A, and mechanically decide whether this is the case. This was the case in the earlier theories. What you did was that you normalized the type, and if it has a normal form, you can check whether it matches the shape of the element here, the program. So he went back to intentional type theory, which I believe is the one that Bob has been telling you about, which had a decidable notion of judgment, and which this decision procedure is the basis of proof assistance such as Coq and Agda. So this is somehow the final version, and so I think I remember him saying that when I came to this version, I found that you get a strong sense that you have it right, that you have defined a canonical object, a little bit like predicate logic. And of course, you can decide for yourself, but I will present this theory here. So I will present the 1986 Martin-Löf type theory, or maybe we should clarify terms a little bit. So I use the term intuitionistic type theory. This is the term used by Martin-Löf himself, often by others, but not by himself. It's called Martin-Löf type theory. So intuitionistic type theory has both extensional and intentional versions, Martin-Löf type theory, so this is somehow the same. I know Bob used the more general term dependent type theory. Which includes all kinds of theories which have dependent types, like the calculus of constructions, the calculus of inductive constructions, the various forms of so-called pure type systems, which is some kind of general framework for dependent type theories. But I will, when I talk about Martin-Löf type theory, I will talk about the term intuitionistic type theory. I will also talk a little bit about the calculus of constructions, which is what the origin of the Coq systems. Right. Yeah, so another thing that happened was when I was in Gothenburg, I told my friend and colleague Thierry Coquin that, yes, I'm going to lecture on type theory at the Oregon Programming Languages Summer School. And he said, good, you can tell the Swedish perspective. So not the Swiss, remember, not the Swiss. The Swedish perspective. So okay, so I thought, oh, what does he mean by that? Yeah, what's the Swedish perspective? Well, it is very much the perspective of Per Martin-Löf and his disciples, including my older colleagues Bengt Nordström and Jan Smith, who somehow started off the enterprise in Gothenburg, and myself. Which is, I would say, an emphasis on foundations, on things like meaning explanations, on the clarity and beauty of the theory. I mean, what has happened during these 35 years that computer scientists have applied intuitionistic type theory is, of course, that a lot of things have been developed in the spirit of what Martin-Löf described here. So we have, for example, now the field of dependently typed functional programming. So, and this is somehow the take on the field that is emphasized by the Agda language. Agda should really be thought of as, future Haskell, or future standard ML or future OCaml or something like that. Better, you know, more sophisticated, especially of course in terms of the type system. This is what the younger guys in Gothenburg, you know, the people who have developed the Agda system, mainly Ulf Norell, who was here last year and lectured, Nils Anders Danielsson, who has written the Agda Standard Library, and Andreas Abel, who is also you know, part of the development team for Agda and working in Gothenburg. They are much more concerned about, you know, how do you turn this into a practical programming language with all kinds of features that you see in functional and other languages? How can you make this language into something which can be really used? And this somehow colors the design of Agda quite a bit. It's a little bit at the expense of the logical purity. So what I'm going to try to teach is basically showing somehow what is the logically central parts, how they are implemented in Agda. Of course, in the course of doing that, I will also explain a number of, so as to speak, programming language-oriented features. Agda is really a very nice language, and it's, you know, it's. I went to one ICFP, and I counted the number of times the word Agda was mentioned, and I compared it to the number of times other functional languages was mentioned. Which order did you think it came in? Which was number one? Haskell was number one. Which was number two? Yeah. Of course, probably competing with OCaml a little bit, you know, but maybe a standard ML fourth. So it's really taken on in the functional programming community. Agda is actually not that great for doing big proofs in. It's not been the priority of the designers of Agda. If you want to do big proof, you should really use Coq. The Coq team, so Coq, I would say, if I may give judgment, is more into the doing things like formalization of mathematics and software verification. And of course, in a sense, Agda and Coq are just two different implementations of the same intuitionistic type theory. But the way the system is used, the whole culture, is much more to sort of support those kinds of activities. I will explain why I think so, but it is basically two different implementations of the same basic idea. There are differences, but basically it's the same. Yeah, so you can see how intuitionistic type theory, which started by Martin-Löf's aim to, as he says, clarifying the syntax and semantics of constructive mathematics, led to this language which is now used in a number of different ways. And maybe I should say why I consider these two different. So here is more like you have a piece of software, perhaps written in some other language, and you model that software inside Coq. Here you more directly program in the language. I think there is such a distinction. By the way, of course, interrupt me with questions if you like. And I follow Bob in saying that you're only allowed to ask stupid questions, because stupid questions are usually the ones that make the legs shake of the lecturer. Because, wow, it's a stupid question, I can't even answer it. If you have more, so you can ask anything. But we should, as Bob said, we shouldn't get into detailed long discussions about advanced stuff. You can do that in the breaks. Right. So this is a little bit of background. Yes. I think I've spoken too much about Sweden. Certainly Martin-Löf has been very important for this movement, this period between 1971 and 1986, when he sort of found the final version, was of course very important in going from nothing to some big movement in type theory. But there was a prehistory, and let me just mention the names of the people who should have credit for being predecessors of Martin-Löf. So I think, and so some of them are Americans, so you know, should be proud of them. So for example, Howard, Chicago logician who, for the Curry-Howard isomorphism, who realized that you could extend type systems to dependent types, and in that way you could get the isomorphism between propositions and types, formulas and types, even for predicate logic. So he is of course very important, and he gets a lot of credit. Another very important person is the Dutch mathematician De Bruijn, who did the automat system, which is also dependent type theory, very early, around 1970. De Bruijn was not so much interested in foundation as formalization of math, and he's using his system for classical mathematics to a large extent. Another important person was the great logician Dana Scott, who wrote in 1970 something which looks like a draft of Martin-Löf type theory called constructive validity. There he defined something like an extensional type theory. It's a very interesting paper. It's sort of funny syntax, but for something which is very much the same as Martin-Löf type theory. At the end, you know, he says, well, I discussed this idea with Gödel and Kreisel, and they convinced me that because of the undecidability of this judgment, it was not a good idea, so I abandoned the project. It's a very historically very interesting paper, but it's of course not got the precision, the proof theoretic analysis, you know, or the meaning explanations that Martin-Löf then added to it. But certainly this was also a very important step. Scott gives credit to Dybjer, that I think Ed mentioned it in his lecture, the father of categorical logic. Yeah, so these three people are Americans, he's Dutch. So he defined the notion of hyperdoctrine, which is what I think Ed talked about, Ed, yesterday. Yeah. Ed said he didn't call it hyperdoctrine, but it's a model of predicate logic, categorical model of predicate logic. In this categorical model of predicate logic, you have, I don't know, Ed might have drawn a picture a bit like this. So here, down here, you have kind of types, and types as object and terms as arrows. Up here, you have propositions, and you have entailments. And those entailments, are arrows in a category. So in a sense, what you have here are somehow the arrows in the so-called fibers. They are like proof objects. So Dybjer somehow independently came to the idea of proof objects by categorical considerations. And as regards the rules for quantifiers, Scott credits Dybjer for his, he took Dybjer's rules. So, so there was some very important prehistory. This all happened in the last years of the 60s up to 1970 something. And then somehow there was the development of Martin-Löf, and after 79 things got into computer science, and then, here we are. Okay, so this is a little bit of history and background. I should also, by the way, say I'm not really an Agda expert. I know a little bit of Agda, but to my help I have Andrea Vezzossi here, who is a PhD student in Gothenburg. So if there is an Agda question that I can't answer, then I'll ask Andrea, and you can ask him, and he will help in the hands-on session this afternoon. Yeah. So Adam, who is going to give the next lecture on Coq, he and we have decided to split the hands-on sessions. So today is a hands-on session for Agda. Tomorrow is free day, right? Monday will be hands-on session for Coq. And then there will be, is that Agda? Yeah, Agda on whatever it is, Tuesday. Yeah. And then there will be another Coq session. Yeah, so I have put up some exercises also on this web page. Some Agda exercises. I hope they will be of appropriate difficulty. There are some very easy, some very difficult. It's all to get you started with Agda. You know, you can do more easy things of your own invention. I mean, in a sense, you know, what one can do as exercise is basically, you know, A, implement a beginner's book in functional programming. B, implement all of mathematics you did in school. C, you know, because basically what you can do is that you can implement especially all kinds of functional programming. Well, Adam will also talk about proofs of in Hoare logic, you know, of imperative programs. You can do that kind of thing too. You can somehow do everything as long as it's suitably constructive. But most things are. Most things are. You know, it's of course in analysis and so on. You know, it's not quite so straightforward. But a lot of things are. In particular, you know, I don't know of any convincing examples of practical software verification which is not constructive. So it's much less of a big deal than one might have thought. Okay. Yeah, so I thought I'll turn this on again. Yes. Yes. Great. Yeah, so now will come what you have been waiting for, some Agda code. So, yeah, while this is warming up, I will So I've heard that you usually don't take breaks. Would you like to? No, okay, because it would be an appropriate moment for a leg stretcher. But if you feel okay, you know, I'm okay with continuing to lecture. So let's see. So laptop 2. How did you get it? Laptop. This is laptop 1. Oh, yeah. Like that. Okay, so now it should come. Thank you. Yeah, so I will actually need to write again a little bit, a few things. Yes, so I told you I will I will explain you the intuitionistic type theory of 1986, which is intentional. It has a decidable notion of equality. It's based on a logical framework. So the idea is that somehow the theory is, yes, logical framework based. So the idea is that the theory comes in two stages. First comes the logical framework. And this is nothing but dependently. I'm sorry for those of you who are, I don't know, can you see? Yeah, it's been very angled. Dependently typed lambda calculus with, okay, laptop 2, okay, oh, sometimes it just, see if that helps. With a universe set of small sets, small types, perhaps. Great. Oh, yeah. Yes. So first you start with this very core theory. It's, you know, like the typed lambda calculus, but it's now with dependent types. I'm sure Bob has shown you the rules. And then you have first one base type, the type set of sets. And you have a rule which says, you know, that each set is also a type. So those are the base types, and then you can form by function, you know, by function space construction. So let me write the grammar for this. Yeah, so sorry, this is maybe should have not. Is it possible to just raise it a little bit? Oh. No? Okay, well, maybe it's not too bad. With this one I shouldn't. This will make you sleep, yes. So. Okay, so now at least it's not in the way for you. So let me just write the grammar of the logical framework. Maybe I should do it up here. You know, in the simply typed lambda calculus, we have one syntactic category of types and one syntactic category of terms. In dependent type theory, when we have so-called universes a la Russell, have Bob talked about this? So universes a la Russell is when something which is an element of the type of sets of the universe is also a type. So-called universes a la Tarski, they distinguish between these and have some special syntax, the elements, the type of the elements of the set, right? But Agda uses a la Russell. Okay, so when you have type theory a la Russell, you mix types and terms, as you see here. So the grammar of terms is the following. So, you know, first we have lambda terms. And let me immediately write them the Agda way. So lambda abstraction is written like this, with an arrow. And in Agda, you can use Unicode. Yeah, so you see this lecture, it mixes high and low. There is the foundations of mathematics, and then there is how you input Unicode. This is, \lambda. Often the Unicode is input by doing the corresponding LaTeX, LaTeX macro for it. And this is 2. I mean, you can write ordinary backslash, or you can write dash greater than. Yeah, Adam?
If you're being explicit about the definition of the type theory, wouldn't you want to put a type annotation on the parameter of the lambda? Otherwise it won't be decidable.
So Agda gives that option, but the type theory is still decidable, right? This is, Agda checks such things. This is somehow the main form. So I
don't believe it's decidable if you leave out the type annotations on the lambdas. There's some heuristic that tends to figure them out, but it's not universal.
So you think so? Okay, so I was under the impression that it was. Maybe we should try to find out afterwards and see if we can be sure about what the situation is there. Yeah, so I will also show you some variants. It's actually possible to write out the type annotation in that way in Agda if you want to, but it's not enforced, and people tend not to do it because people will want to write as little as possible. So, yeah, and another thing is that in Agda you need to use a lot of white space, so there needs to be white space between those two here. I'm not sure actually there when I think about it. So yeah, so I think there too. Anyway, then there is application. So those are the lambda terms. I mean, this is just the terms of the untyped lambda calculus. Then there is the type of sets. This type of small types. And then there is the dependent function space written like this. This is basically the language. And then the typing rules. Yeah, so I already gave some, but for example, the typing rules might be good to write down for, where should I write them? Maybe over here. Like that. So, and then you have another rule, which is the following. So both small types and large types are closed under dependent function space. So actually Martin-Löf rejects this rule. And in that way he's not very happy with Agda because Agda implements it. Pure type systems classify systems according to exactly which dependent type function spaces you accept. And in calculus of construction, we have a further rule. Maybe I should use a little letter there. So in calculus of constructions, this is called prop, but it plays the same role. This is an example of an impredicative function functions, in predicative universe, because you define here a type, a set by quantification over all. By quantification over all. Sorry, that was wrong. Over the collection of which it's already defined. So this is there, and this is rejected both by Martin-Löf and by Agda, and I should show a little bit the consequence of this. It's got very important consequences for how you use the theory. Anyway, so this is somehow the theory. This is the very, very small core theory. Then the second stage is the introduction of inductive types. Special sets. And this I will talk a lot about because, of course, my lectures are called Inductive and Inductive Recursive Definitions in Intuitionistic Type Theory. So I won't say very much more about this at this stage, but I will talk about it a lot later. So Martin-Löf, in 1986, when he decided on this theory, he decided to call the fundamental notion of type, and the small types he calls sets. And consequently, alternatively, he calls LF the theory of types, and the inductive types the theory of sets, or data types, if you wish. So I should say that in around 1986, Martin-Löf had one version of a logical framework. There was another version in Edinburgh where Bob Harper was in the team who devised this. This led to, I think it's the basis for the 12 system by Frank Fenning. Correct story, Frank? Yeah. Quite. I should also say, why this logical framework? Why is it called logical framework? Well, am I telling you too much history? No. Good. Why logical framework? Well, the reason was that in the 1970s, important things happened in proof assistance. It wasn't even called proof assistance. There was, for example, the Edinburgh LCF system, which was an implementation of a logic based on domain theory. But it was, a very successful and important thing done. There were various efforts here in the United States. But people implementing such systems felt that they over and over again would have to implement, things like some notion of variable substitution. It was done over and over again. So why not instead have some kind of meta system where you have some fundamental notion of abstraction and application, and then all other, all systems with a standard notion of variable abstraction could be implemented on top of that. That was an idea that grew very strong in the early 1980s. For example, Robin Milner behind the LCF system was very much behind this force. And this led to the interest in creating logical frameworks where you could implement not only, intuitionistic type theory, but other logics like higher order logic used in the Isabelle system, set theory used in the Misar system from Poland, for example. So this idea became very popular, and I will show you maybe later today even, or this afternoon, how this logical framework level can be used to implement some other logics, like higher order logic, like classical higher order logic. So although the system is so very small, you can stay within that system and do a lot of things. And you can use Agda in that way. It's not entirely adapted to it, but it's surprisingly well adapted to it, I would say. Okay, so those are the rules. So now, finally, a little bit of programming. Yeah?
Can you just hit that first rule there? Can you say that?
this rule here. Yeah, this rule is, it's the typing rule for dependent function space. If you can build the type of functions from x in A to B, where B may contain x freely, provided the type of the source type or domain type actually is a type, and for each element in that source type, we have a well-typed, a well-formed type. This may also may contain the x. In that case, this dependent function space is well-formed. Yes. Oh, John, hi.
The other question I had about that first rule, you said that Martin-Löf rejects the second.
Yes.
So how does, aside from the notation, how does that differ from the rule for the Cartesian particle family of sets in like Nordström's book?
Sorry, the question is, how does that differ from?
From a rule which he does accept, because like so in the logical framework you encode that rule by introducing a constant.
Yes, that's right. Yes.
How does that differ?
Oh, you mean how you? Yeah. So how does it differ? I mean, it's of course literally different that he instead encodes that rule through a constant. Are you asking whether they can be, the two systems can be translated into each other or not?
I guess what I mean is that if you first added the constant in the logical framework, then that rule is evident.
Yes. So so of course in the logical framework, maybe we should come back to this a little bit later, but I think you're making a good point that it's perhaps mainly a notational variant, in the sense that you could actually derive a very similar rule. It would just have some kind of constant prefaced. So I will actually show something like that a little bit later. Yeah, so constant. So the way things will happen, I mean, even in the ordinary simply typed lambda calculus, one typically works in the following way. You start out with just the rules for forming functions by lambda abstraction, application. You have typing rules, you have function types. And then you enrich your language by introducing a new constant, like, for example, 0 for the 0 natural number, or successor for the function from natural numbers to natural numbers. So then, so you add these constants to your language and you let them participate in the rules for the language. So you add, you have some. You add to the syntax of your language some constant c, call it c, and then you have new typing rules, like that. And sometimes you also have new equations for them. And this is exactly how you typically work in functional programming. You introduce a new constant for the append function and the definition, some equations for it. And this is exactly the way it works in this logical framework-based style. We introduce a new constant and its definition. Yeah? Okay, so why doesn't it come on? Laptop is showing. Let me see, so. Yeah, I don't know. Let me, do you think it will come out now too? Okay. Oh, I see, yes, maybe that's the problem. Yeah, so now at least my screen is not blank, so maybe that was the problem. Yeah, so so I now will start by doing a little bit of just showing you the first steps in writing an Agda file. Yeah, there it is. Okay. Okay, now we go here. So when you write an Agda file, an Agda file is always a module. So you have to start declaring the module. So let's just call this module introduction. And then you have to write where. And then you have to save it. So here, so we save it in a file with the same name, .agda, and then you will get Agda mode. Have you tried to download the Agda system yet? Because that may take a little bit of time sometimes. And then this is a file in the LF directory, and my Agda search part goes to that parent directory. So this shows that this file is in the file introduction.agda is in LF, and so you have to instruct Agda there too, unless your search part goes directly to that part. And now we have a correct Agda file, and we can do. We'll turn this off. And you see, when it type checks, it becomes colored. It makes you happy. This is what makes Agda programming so satisfying. That it's color. It's correct. Okay, so now to your question here, we should define a constant in pure LF. Okay. So we should have something C of type A, and then C equals something. But what types do we have? So this big A is something that we must already be defined. A good type. Can you think of a good type? Yes. Can you think of an element of the type of sets? There are none. Bad luck, because we haven't introduced any. They all come in the theory of sets, which I will come to later. So we actually have to have a more sophisticated type, like set to set. So call it just I don't know, id set. And here is the definition. I have to type for her. I have to be good at typing. Here it came. Do you think, will it color? It did. Okay, so we have written our first function. So here you see exactly, you have to define the type, a new identifier for the constant, and define it. Let's write the ordinary identity function. So, in Haskell or something, one would just write polymorphically A to A or something. But here we have to make the polymorphism explicit. So here you see the first use of the dependent function space. So what this type says, is that for any small type x, we can define a function which maps x into x, namely the identity. Yeah?
How do you write a comment in Agda? If I wanted to take some double.
Yes, double dash or like this, like that, or like this. Yeah. So so of course, we have the usual standard convention of association to the right of the function arrow and so on, right? So I hope I don't need to explain that to you. And similarly, we can have we can bind several variables. So let me just check that this is taken by Agda. It was. Yes, you see here that this is a kind of explicit form of polymorphism where we actually have to give the type of the identity function as an argument. So the function which takes a small type big X, an element of that type little x, and returns little x. And Agda, maybe I should just tell you that immediately. Agda allows wildcards, so you can, since we don't use the big X in the right-hand side to the right of the arrow, we can just write a wildcard symbol. We can, of course, also use somehow functional programming style of definition of lambda expressions, like this, or with wildcards, like that. Yeah, so this you will never forget, but let me write it down again. Control C, Control L is load, type check the file. There is also a menu, as you can see up here, with various commands. And yeah, and of course you should also go to the Agda wiki where you can find answers to a lot of your questions. For example, there is a list of all the commands that you can interact with Agda with.
I'm sorry, Peter, which ID do you use with something like mark command?
Sorry, which is?
IDE. It's like Emacs command. IDE.
Oh, she's asking, are you using Emacs?
Yeah. Oh, I'm sorry. Yes. So Aquamax is a version of Emacs, and you have to, you interact with Agda via the Emacs interface, and so Agda has an Emacs mode, an Emacs Agda mode, and you need to download all this and set it up right. So before you can program with Agda. Sorry, I should have said this. Yeah. So that's the identity function. Yeah, so the next important thing to write is that because we have this somehow explicit form of polymorphism, things can become very verbose if you write complicated programs or maths. And therefore we have to have something which resembles the polymorphism that you have in ML or Haskell style languages. So there is something called the implicit function space. The implicit function space is denoted by curly brackets instead. And then you, it works here too. But this we don't have. This is just for Coq. And then the argument, you don't need to give the argument. So if this is instead the implicit function space, then we can omit the type argument. So you have to change the typing rule, right, so that you don't need to mention the big X as an argument to its identity function. And of course, so this makes it possible to program in the style which looks like polymorphic functional programming. Yeah?
So if I define the capital X implicit, I cannot use it in the definition of A.
So when you program in Agda, you very often find yourself asking the question, should I have this argument explicit or implicit? And it's a bit difficult to predict, will I want to see it or will I not? So Agda helps you in that way, saying that if you made the wrong decision, you can still put it in. You can enclose it in curly braces. And you can use a different name then, right? And if you want to put in some of them and not in, not maybe, then you can write something like this. If you want, this means that the X argument will be instantiated by the Y. So that's how you can recover implicit arguments without needing to change your functions.
But you wouldn't actually write that in the definition point like this. You'd write it at the use point.
Yeah, typically, of course. Not always. I mean, this feature is sometimes useful as well in the definitions, but usually when you use it. Right. Yeah, Frank?
Does it mean that Agda does not satisfy alpha conversion?
Sorry, that?
Agda does not satisfy alpha conversion. You can refer to the bound variable there in your review.
I think this is a question that I don't know the answer to.
I think the short answer is yes, but it's not an interesting flaw. It's just a syntactic shorthand, and the particular variable choices from the original definition guide how the shorthand is interpreted, but it doesn't impact the type theory.
Maybe I should write this down. List of questions.
Probably only works for named identifiers, so it's not a first-class thing.
Yeah, that's kind of these implicit variables behave like labels in a regular factor.
You can also just omit the label. You just delete the X equal and you use Y in the middle there. The implicit arguments will still work if you put them in the right order. You use the names whenever you're trying to pick some specific one out of some long.
Right. Yeah. That's the reason for this feature. Right. Okay. So another thing that I should show you is how you actually compute. There is a command called Control-C, Control-N, which is normalize. So for example, we don't have much to normalize at this stage, but let's do the little we have. Control-C, Control-N, and then you see that down here, we can write an expression. So for example, what can we write? Id applied to id. And you see, it quite cleverly computes id. So this is somehow the poor man's version of running programs. There is an Agda compiler as well, right, for if people want to do somehow serious serious running of their Agda programs. Of course, admittedly, with Agda, we do a lot of type checking, but not very much running, you know. But in the future, within the next 5 and 10 years. Okay. So is there? Ripple. Sorry? Yes. Let's see.
There is Agda interactive, dash interactive, but it's not the main interface we use. So you use it for your own reason.
Right. So there is such an interface, but yeah. So that should be also on the Agda wiki, right? Yeah. We could check that. Yeah. So the Emacs interface is the main one. Okay. So yes. So now we have done that. Let's see, how am I doing for time? Quite close to the end. What else can we do? Oh yeah, before we leave, I think I want to show you what is really the main feature or contribution of the sort of Agda style interface. I mean, Agda had a precursor called ALF for A Logical Framework. The first version was something like 1990. And it was really something which was the efforts of Thierry Coquin and a guy called Lennart Augustsson, who is a big, strong functional programming guy, implementing some ideas of Bengt Nordström, one of the pioneers in Gothenburg of type theory, where he had the idea of constructing proofs in type theory by pointing and clicking. So the idea was that, you've probably seen it because it has spread, but say that we want to define composition. Let me now introduce another feature here. So you can write mix-fix operators by declaring the syntax in this way, 1 underscore for each argument, each explicit argument. And then when you use it, you have to put white spaces in between the underscores and the other symbols. So let's see what is the type of the composition function. Well, it's if we have a function g from y to z. See, I'm not very good at typing. So it's a polymorphic function, so this is the case for any x, y, z, which are small types. Yeah, so here you see, for example, also another feature that you can write repeated function space in this way. This really means x for x in set, for y in set, for z in set. You can write them all together like that. And they are all those 3 arguments are implicit. And then you have the 2 explicit arguments. Then you write the definition like this, and let's do it in functional programming style. So you want to know what g of x is, but then you can apply it to an argument. And now, normally you would write out the definition of this, but Agda lets you say, I don't yet know. And now that I type checked, it took the question mark and turned it into a hole, something where you need to place the expression. The point of this is that you can do this gradually. You put the cursor in the hole, and now you can do, either you put in the complete expression, g of f of x, and do a command called give, Control-C, control space, give complete expression in whole. But you can also do Control C, Control R, which is refine, where you can do either of two things, either by outermost function symbol or by partial expression. So here I could do control space, but I can also just write G. That's the outermost function symbol, and I do Control C, Control R, and you see that it turned the argument of G to a new whole. And then you can put F, etc. But you can also write a partial expression like that, G F of question mark. Or if you did like this, if you didn't know what the arguments of F was, then you could, it takes the partial expression with the new wholes and type checks it. So actually the type checker for these partial expressions is of course a refinement, a more sophisticated thing than the usual type checker for the language of total expressions. You can really start with something like this. And if you even find the type hard to write down, you don't even know what your program is going to do, but you gradually have to come across it. Agda lets you do this, and it keeps the consistency of the type and the term. Keeps that in order. Sorry, I have 3 minutes too much. Yes.
The bottom buffer, it shows the types of the holes.
Yes. Yes. So So Agda has a special kind of arguments, dotted arguments. I think maybe I should take that the next time. So here we have. I mean, this means that this is some type argument which is equal to x. And then here you see that it doesn't actually know this, and this is something about universe polymorphism that I don't want to get into now. But I mean, basically in the window here, you will see the type information of the different holes, and you can have any number of holes open at the same time, although it's not a good idea. Okay, thank you. I will see more of you this afternoon.